I'm Holly Cummins. I work for Red Hat and IBM both. It's very complicated. I'm part of the Quarkus team. And a while ago, I had this idea that it would be a really good idea to do a talk that just had loads and loads of demos. It turns out this was actually a really terrible idea. Top presentation tip, never give a talk with lots of demos. It's very stressful. But we'll see how we go. So I want to talk really here about some of the things that you can do with Quarkus that maybe are a bit off the beaten track, that you're not using every day, but that can be quite fun and kind of useful. Just as a sense check before we start, how many of you are using Quarkus now? A couple of hands. How many of you, of those two hands, how many of you are using Quarkus in production? No hands, okay. How many of you have heard of Quarkus? All of you, excellent. So I'm sort of going to assume that the rest of you are sort of somewhere in the middle of not using it in your day-to-day yet, but think it's quite cool, would like to hear more about it, would like to start using it. Excellent. Okay. So the first thing that we're going to talk about is a very good follow-on to this morning's keynotes, because I'm going to show you how you can save the world with Quarkus. Not in a general sense, that would be a little bit too ambitious, but it turns out that Quarkus has a very interesting green IT story, because climate change is obviously something that we should be thinking about. And I think when you sort of, a bit like what they shared in the morning keynotes, when you look at climate change, it's easy to have this sort of initial response of, oh gosh, that's really terrible, and it's so terrible that it's nothing to do with me. But actually, when you look at, even before AI, when you look at what is going on in IT, the IT industry and the digital world in general are responsible for using a lot of electricity and a lot of hardware. And so, by extension, they are responsible for a lot of carbon. And we tend to think of aviation as the kind of the poster child for climate irresponsibility. But when you look at this, you can see that IT, the digital world, is actually responsible for more carbon than aviation. And on that previous slide, digital world sort of includes everything. So it includes the PlayStations, it includes the iPhones, it includes some of the stuff that's maybe a little bit peripheral to what we do. But for us as software professionals, if you look just at data centers, I think this is really relevant to us, because in general, what most of us do is write the software that runs in the data centers. Again, excluding AI from this whole conversation. And if we're writing the stuff that runs in the data centers that is responsible for the carbon emissions, that's kind of terrible, but it's also really, really good, because one of the problems when we think about climate change is we think, oh, there's nothing I can do. But actually, when you look at this, there is absolutely something that you can do, because if we're writing the stuff that is running in the data centers, we can change what we're running in those data centers and therefore reduce the carbon footprint. And this is where Quarkus can help as well. Again, excluding AI, what can Quarkus do that might change any of this? Well, Quarkus is very energy efficient. And I had this bright idea. I'm definitely one of the people who is all for creativity, again, like we saw in the keynote. Some of my ideas are good. Most of my ideas are truly terrible. And so I had this idea that it would be really, really fun to show how energy efficient Quarkus was by powering a Quarkus application server with a lemon battery. Because if you take a lemon and you put sort of a bit of zinc into it and a bit of copper, and then you sort of connect it with an electrodes, you can get power. And I kind of had this idea that, probably one lemon wasn't really going to be quite enough. I thought I might need a handful of lemons. And then I started to look into it a little bit more, and then I realized that maybe I was going to need more than a handful of lemons, and maybe I was going to need sort of a lemon battery array, a bit like this. And then I looked into it a little bit more, and I found a YouTube video where someone had done something very similar, but with potatoes rather than lemons. And I thought, oh, great, I can just follow through these along with these instructions, substitute lemon for potato, and I'm good. And I was feeling really encouraged until I got to this bit, where he had used 9,000 potatoes in order to power his potato computer. And the logistical challenges of this were not good, because he had to sort of turn the potatoes into a slurry, and then he had like 9,000 pounds worth of, or 9,000 potatoes as sort of liquefied potatoes in his home office or wherever, and they started to rot. And at this point, I was really, really questioning the feasibility of this demo. And I did some more math. So with Quarkus, with a lemon, you can get 0.0007 watts. And I sort of, worked backwards from that to what energy consumption I might need. There's a slightly outdated, but still really fantastic data set that a company called TEEDS prepared a while ago. And what they did was they looked at all of the AWS instances and worked out how much energy they would use. And I could see that you can run a good Quarkus app on a T3 Nano instance. That needs 12 watts. So what that would mean is that I would need 17,000 lemons. So at that point, 9,000 potatoes was starting to look really good. And as well, what I wanted to do is I wanted to show a comparison to Spring, because Quarkus is efficient, and it's not just efficient in a vacuum. In particular, it's efficient compared to Spring Boot. So with Quarkus, it would be 17,000 lemons for my demo, and if I wanted to show it for Spring, it would be 40,000 lemons for my demo, and so if I wanted to do the two of them, it would be 60,000 lemons. So this was not good. So what I'm going to do instead is I'm going to do a demo, which is already a crushing disappointment because it doesn't involve a single lemon, but I will show it to you anyway. So let me bring up my code. So what I've got here is sort of a preliminary version of some work that our team has been doing on energy measurement. We did, a couple of years ago, we did a set of experiments where we looked at our energy consumption, and we published that, but I wanted to do a refresh of those results, and I also wanted to have something that could be run just on a local laptop as well. So what I've got is a colleague of mine has written a tool which abstracts away from hardware level tooling for measuring energy, because there's various ways that you can measure energy. If you're using Intel, there's a tool called RAPL. If you're on Mac, there's actually a more powerful tool that can isolate it down to the process level and give you that. But if you start to look into this, it's a lot. So my colleague Christophe Laprin has sort of written a tool which abstracts away from those, and you can just say, please use my energy harness and then start this application. So what I'm going to do is I'm going to use that tool. I've got links at the end with all of these tools, and I'm going to run my Lemon Power, and you can see I'm running my Quarkus application, and I'm going to start it up. And what it's going to do is it's going to first start all of the dependencies. So it's going to start a database as a separate process. Normally with Quarkus, you wouldn't necessarily do that. You'd run it as a dev service, so Quarkus will take care of starting a test container with your database so that you don't need to worry about it. And it's going to start an OTel stack as well. And then it's going to fire off the energy measurement harness. You can see I need to enter my password here because it's hardware level instrumentation to collect the energy. So this is ready to go now. And so now I'm going to drive some load into it. So this is going to put in 20 seconds of requests with 100 connections, and it's just going to run it, and then it's going to stop it. So it's done all that, and if I go back over here, you can see that I've got a result. So I have 53 watts of power consumed for this little benchmark, and it would be that many lemons. So I can do the same thing for Spring. So again, I'm going to run my Spring Boot jar, and it will start up the stack as a separate thing, start up OTel, and then once the OTel containers start, it will ask me for my password, which shows that it's ready to measure the power. And then I can go over here and I can run my stress test for 20 seconds. And then it's done that, and then I should have an answer. And you can see that I've got more lemons. So I've got 74 lemons instead of 54 lemons. So I didn't successfully use real lemon batteries, but I did successfully measure energy. If you would like the source code for this, it is there. So was this an easy demo? It worked, which is good. But there was a couple of problems with it. So the first one was that sort of initial practical problem of I couldn't bring 77,000 lemons in. The second problem is that the tooling I'm using is still pretty bleeding edge. You know, this is something that I think our industry needs to be sorting out. It needs to be working on it. We're still developing it. And you saw as well that because this is sort of new tooling, I had like one window where I was driving the load and one window where I was running the harness, and I was having to flip between them. If I was a little bit slow, then there's probably an extra period when my application is running and consuming energy without load, but it's still consuming energy. So, you know, I wouldn't necessarily put these results in like a peer-reviewed journal. There's a couple of other problems with them as well, which is it is a general principle of performance measurement, and this includes energy measurement, that you shouldn't do it on a laptop because the results are totally non-reproducible. I'm generating load on the same machine. I'm not counting that in my energy consumption because the Apple tooling does allow you to isolate by process. And I had that manual coordination across the windows. So this is basically a pretty dodgy test, but I think it does give you the idea, which is that your electricity bill will be lower with Quarkus. And that's kind of okay. And there's another thing that is I take a lot of comfort from here, which is when you're doing these kinds of measurements, what you always want to be doing is trying to validate it against something else that you have more confidence in. And it is not always true, but it is very often true that having a higher throughput corresponds to having a lower energy consumption, or at least a lower energy consumption per unit of work. And we have really, really good data that shows that Quarkus has a higher throughput. So you can see in this chart here, Quarkus has about twice the throughput of Spring. So the fact that my two results kind of line up, and that the energy saving is sort of, going in the same direction as the throughput results gives me good confidence that, even if I'm not perfect down to the individual lemon, the general flavor of my measurement was pretty okay. But what about sort of other things? So sometimes that throughput, sometimes that energy usage is what you care about. But quite often, actually, the bulk of your energy usage isn't going to be coming from the electricity that's actually consumed. It's going to come at a much earlier stage when the hardware gets provisioned, either by you or by your cloud provider. And hardware has an enormous carbon impact, but it also, of course, has a financial impact. So a lot of the economic advantage of Quarkus doesn't necessarily come from that energy, from saving those lemons. It's about saving cost, saving operational cost, and saving CapEx. So I want to show another thing that sort of illustrates some of the operational flexibility that you might have with Quarkus. But in terms of what you should take away from this, lowering costs, Anne mentioned this as well, lowering costs is a really good thing because it almost certainly means you're lowering your carbon footprint. It almost certainly means you're lowering your energy usage. It almost certainly means you're lowering either your hardware bill or someone else's hardware bill. This is a good thing. And Quarkus helps lower costs, and so therefore it helps with all of those things. But I want to show sort of another aspect of that Quarkus green IT story, which is, I talked about throughput, the sort of the scalability of Quarkus, that on the same hardware, Quarkus can handle more load. But one of the things that Quarkus is really known for, of course, is starting very quickly. It starts very quickly without GraalVM, and it starts exceptionally quickly with GraalVM. So let's have a look at that. So what I've got here is a little application. So this is using Pico CLI. So I've just got a little meme service, and then I've got a little meme command, and then I compile it to native. I'm not going to show you compiling it to native because compiling it to native takes a while. But what I'm going to do is I've got my terminal here. And then if I say, hello, Devox, so if I run that, then you can see it did it extremely quickly and it completed that command. So I can just do it again, boom, done. And now if I look on my disk, what I will have when it refreshes is a meme. So one does not simply say hello Devox, and I can change that. I can say hello London instead, and then that will be. Well, let's close that to force it to refresh. There we go. And I can add parameters as well. So I could say I had a biscuit. And then let's do a variation of the meme. So let's do that. And then if we open that, I ate a biscuit. It was awful. So in terms of going away to production, you're probably unlikely to have a professional requirement for generating memes on the command line very quickly, but you never know. It might give you some, some faster ammunition for your corporate Slack. But there are things that this is useful for. And there's also some interesting learnings from this demo as well. This was also another demo that was sadly not easy. Writing the CLI was easy. There's loads of samples out there. The native compilation was pretty easy. It turns out that because this was doing graphics, and all of the Java graphics libraries at some point then end up relying on Java AWT, AWT does not work on native on Mac. So what I was doing in that demo is I had a little sleight of hand. I had a Linux container in my terminal, and I was actually running it on a Linux container because that was the only way I could make it work. So yes, there is a lesson here, which is that one does not simply do native graphics on Mac. It's hard. Should you wish to try native graphics on Mac, native AWT on Mac didn't work. There's another VM called Liberica, that didn't work. I tried when you do GraalVM, what you end up having to do if you're not using Quarkus is sort of add and remove things to the closed world. I tried playing around with that for a while. GraalVM have a community container, that didn't work. There is a distribution of GraalVM called Mandrill that's produced by Red Hat. That container did work. But really the takeaway here is think about all the cool things. Think about all the cool command lines you can write when it's that fast to start. It means all of a sudden for your command line tools, instead of being limited to shell, you can do things in Java as well. Native is incredibly, incredibly cool and powerful. When I joined the Quarkus team, I spent several days just like starting the native application because it was so exciting to see it start that fast. But native is absolutely not a silver bullet. You can get traps with native. You can get things that are harder with native. Quarkus does a lot of that heavy lifting for you, but there are corners where the Quarkus support doesn't extend to, or where any of the native support doesn't extend to, like AWT. And another aspect with native, going back to green IT, is you probably saw briefly on the chart I showed earlier, Quarkus on native has about half the throughput of Quarkus on JVM. And that's similar for Spring Boot or anything else on native. If you're using the Community Edition Graal VM, there is a very serious throughput penalty there. So native is absolutely worth using in order to get the operational flexibility, if that's what you want. If you have the kind of workload where you want it to have a very low footprint, memory footprint, and the workload is moderate, then native is a good choice. If you want to have the kind of operational story where you're scaling it up and down quickly, native is a great choice. If you want to use it for your daily workhorse load, probably not the best choice. Probably JVM is going to be a better option there. So I said doing graphics with native was hard. That is true if you do Java graphics, but it turns out that there is another way to do graphics in native, which is to not even try and do it in Java. So you can use WASM to do all sorts of things. It took me a while to wrap my head around WASM, but I eventually sort of understood it by analogy with what Java is doing. So with Java, we have our Java code, and then we use our compiler to generate bytecode, and then the Java runtime will sometimes interpret and sometimes compile that code in order to give us this write once, run anywhere experience. And then it may or may not work, depending. Usually my code, it fails the first time. And then, of course, we then got more languages. So we got things like Kotlin that would also allow us to compile to bytecode, or Groovy, or whatever. With WASM, there's sort of a similar model. So we have the WASM representation, and then we have a WASM runtime. And that WASM runtime can interpret the code, or it can compile it. And it may or may not work. Where it gets interesting is the input. So instead of having just a fairly small set of languages like Java and Groovy and Scala, you can have C that compiles to WASM. You can have Rust that compiles to WASM. You can have JavaScript. You have to go 2 steps. You can compile your JavaScript to C, and then you can go to WASM. And so then what that means is that you can run almost anything, anywhere. And then things get more interesting as well, because there's a whole range of different WASM runtimes written in different languages, including in the JVM. So now you can get this situation where you can compile your Rust code to WASM, and then you can turn that into bytecode, and then you can run it in the JVM. If your head hurts looking at this diagram, you are not alone. It gets really sort of circular and weird, all of this. But what I want to show you is a tool called Chicory. So Chicory is a JVM native WebAssembly runtime. So Chicory allows you to take your whatever code, turn it into WASM, and then run that WASM natively in the JVM, which unlocks all sorts of things. So let's have a look. I mentioned that doing graphics was not so good with native. So I'm going to show you a different app instead, which is using a tool called Photon. Photon is a graphics manipulation tool written in Rust. With the best will in the world, you know, there's a lot more graphics manipulation tools written in other languages than there are in Java. So I'm going to start my Quarkus application. Let me just show you a little bit of what I've got. So here I've got the Photon tool, which is written in Rust. So I've got like all my Rust stuff here. And then I've got my Quarkus application, which just has again, sort of a resource and then a service which is calling out. So let me bring up my application. And here I've got my photon image processor. And so what I can do is, let's bring up a picture that I took in the keynote, which is Anne's talk. And then I can run an effect on it, and I can... That was not what I expected in any way. It was supposed to go blue, and it's gone upside down. This is exciting. Let's try... Okay, so we're able to apply these transformations. So you can see I'm adding some padding. Let's try that again. Okay. I don't know. I don't understand. But we're just going to accept that it turned it slightly blue. I think there's not very much white in this image. So that's probably partly why it's sort of slightly disappointing. But I think those got turned slightly blue. So what if I want to take advantage of some of the Quarkusness of it? What if I want to change my application? Well, I can use normal Quarkus, live reload, dev mode with restrictions. Any change I make to my application will be picked up, but most of my application is just calling out to Photon. But I can change it as well. So I'm going to bring up my filters. So this is the Rust file, which I don't really understand at all. But I'm going to change the color of my oceanic filter and make that just 40, make it a slightly different color. In an ideal world, this would be instantly picked up. In practice, there is no live reload for Rust. It is not the sort of thing that language is optimized for. So I'm going to build my Rust file. So I have to build the Rust code, but I don't have to build anything else. And then when I go back here, I will reload that. And then let's bring in that image again. And then let's try applying the oceanic effect. And yeah, I think that, well, it went upside down, which I cannot explain. But it did go slightly purple. So I think I'm going to call that a success. And so let's stop that. So code is there. This ended up, despite being completely weird, this ended up being the easiest demo of all of them. Running Rust in a JVM, it was really easy. It just worked. When I wrote this demo, we didn't have a Quarkus extension, so some of the stuff to do with live reload, I had to do a little bit of hand tweaking. We now have a Quarkus extension, so you get all of that for free. This kind of use case of running Rust in the JVM, I struggle a little bit to know how very practical this is. Are you really going to be going away and doing this? But this kind of technology, well, this specific technology, in fact, is being used for things. So for example, if you're doing contract testing, you might be using microcs. And what microcs do is they allow you to do, that's a Java tool, and they allow you to have JavaScript scripting, and the way they do that is with this. So they take the JavaScript, they wrap it in Chicory, and then it allows them to run it inside their JVM engine. So this can unlock use cases, it can unlock user flexibility. And Andrea, my colleague, who is one of the main developers on Chicory, he says that running JavaScript in a C runtime compiled to WebAssembly on the JVM is the new black. So you heard it here first. This is what all the cool kids are going to be doing next, is sort of this extreme polyglot. And again, I think the thing that's sort of interesting about this is how it just unlocks extra options that you maybe didn't have before, and it just gives you a situation where the language something is implemented in doesn't need to be a barrier, and you don't need to, go convert it to the language that you want using AI. You can just run it as it is because the tooling is there for that. So, having said that you don't need to convert things, you can run Rust in Quarkus. You can also run Spring code in Quarkus. If you have a Spring application and you want to get to Quarkus, you have a number of options. So we have documentation explaining how to do it. But what I want to show you is one of the sort of the funnest ways to do it, because it doesn't involve really changing the code. So if I go back here, so this is the same repository that I did the energy measurements in. I'm just going to go back to a slightly older version with a different branch. And you can see that what I've got in this repository is I've got a Quarkus application and I've got my Spring Boot application. And so I'm going to take my Spring Boot application. I'm going to, well, we can have a quick look at the POM. So you can see we've got our normal Spring Boot POM. I'm going to delete that. And what I'm going to do is let's clear this, get rid of the lemons. And let me just get that. So I'm going to bring in a POM that I made earlier into my application. So I'm going to bring that in, and I'm also going to bring in, I've got a resources file, which is very springy resources file. And I'm going to bring in a new resources file here. And so with those two changes, you can see I've got slightly different config in my resources, and I've got a very different POM where instead of having my Spring dependencies, I've just got Quarkus dependencies, but I haven't changed the code at all. This is just the same Spring application as I had before. But now, because I have my Quarkus POM, I can do Quarkus dev. Oh, what has it done? Okay, let's just get rid of this again. This is going to be a very disappointing demo if we can't get past the first step. So this is the version that lives in the repository. So we'll just bring that in. And let's do a clean. Oh, wrong directory. I was building at the top level, and I had duplicated my POM. Right, let's try that. OK, so it's still failing, but the good news is this failure was expected. So there's a bunch of stuff in the Spring application file that we don't really know how to deal with. So we've got this, where is it, org acme. Oh, I'm still in the wrong project, sorry. So here I've got, in my Java, I've got my Spring Boot 3 application. It's just got springy stuff. So if I just delete that file, so in Quarkus you don't need that top-level application file. And if I run again, let's make sure we've got the clean. Then this starts, and you'll notice a couple of cool things have happened. So first of all, I need a database, and it's started a database because I didn't have one configured. And now if I do D, I can bring up my dev UI. And if I go back here, I can bring up my application as well. And then I can hit my fruits endpoint. And I've got it working. I won't do it because I won't have time, but there is a follow-on to this that I can do, which is to combine it with that performance testing that I was showing you. Because just by changing the underlying framework, my exact same application code starts faster, and it will also have twice the throughput and half the energy consumption. So the code is the same, which is cool. So let's just, oops. So let's stop that. And I will just, as well, just to show that I'm not cheating, let's roll back these changes. And now let's do a Maven install. Oh, I only rolled back one. Thank you. That would have been cheating, wouldn't it? Really? OK. So let's Maven install. I should have skipped the tests, really. And then if I do Java -jar, target, Spring Boot 3.jar, then you can see I've got my Spring application starting. So the code really is Spring code. And I think it's complaining because it doesn't have a database because there's no dev service. So this was another demo where it was actually really easy. The applications were pre-existing, and so it's just a fairly easy step to just change the POM to use the Quarkus libraries instead. There are a few little things in there. One is that we have compatibility libraries for the application code. We don't for the tests. So the tests you do either have to convert manually or do something else with. I should say as well, you'll notice that I went back to a slightly older version of the code. We'd added level 2 caching on Hibernate, and it might be possible to do that with the compatibility libraries, but I don't know how. So I just went back to the version that didn't have the Spring compatibility libraries. So it's definitely playing with the compatibility libraries is a good thing to do. We aim to cover about 80% of the cases. If you're in one of those 20%, then you will have to do some work. But of course, there's lots of ways to get from Quarkus to Spring. So there's the compatibility libraries that involve changing no code at all. We also have migration tooling. So there's open rewrite recipes that you can use, and we are working on more skills as well for if you want to use AI to do it. Speaking of AI, I've got to my 5th demo, and I haven't mentioned AI yet, so I feel compelled to do an AI demo. So I want to talk about LangChain for J, because often when we talk about AI these days, we're sort of talking about AI coding assistance. That's obviously really important. It's something that Quarkus is investing in a lot. So we have a Quarkus MCP server, which is quite cool. And there's various other things, I think, that will reduce the cost of using AI because of having really sort of smart Quarkus-specific tooling to integrate to your AI development assistant. But I think AI has potential beyond just helping us write code. AI has potential in our applications as well. And the deeper we can integrate AI with the applications, the better the output is going to be, the better the value is going to be. For us in the Java world, a lot of the generative AI tooling and stories out there is really, really Python focused. And I did not become a Java developer in order to write Python. This is starting to change now, so we're now seeing a lot more Java AI tooling, which I think is really important because so much of the software in the enterprise, so much of the integration in the enterprise is in Java, that the more easily we can integrate to that existing ecosystem by using the same libraries and using the same solutions for those problems that have already been solved over and over again, it makes sense. Because AI is ultimately, enterprise AI, certainly it's an integration problem. So LangChain for J gives you support for things like using output in your code, sort of standardized prompt structures. LangChain gives you that. LangChain for J also gives you that with the Java bindings. That is often not going to be enough for proper programming. So what we have in Quarkus is we have a set of integrations for LangChain for J that give you things like the failover, the integration, the dependency injection, and all of that is Quarkus LangChain for J. So let me quickly show you what we've got. So I've got here an application. So this is just so far a vanilla application. I've got a front end and I've got a little back end that just does, it's got some endpoints. So if I look at that, and this is another cool thing that this is using. It's using a Quarkus library called Quinoa. And what Quinoa allows you to do is integrate your front-end development flow with your back-end development flow. Because quite often when you do that, you have to sort of figure out, okay, well, where do I put my source code and how do I compile and who sort of proxies to who? Quinoa just takes care of all of that. So I've got my front end, and the scenario here is that I would like to provide a concierge service for animal adoption that suggests animals, but I have no animals. So I can fix that. So in my backend, I can inject. So you can see I've got that dependency injection. I can inject my AI helper. In my AI helper, I'm going to use register AI service. So again, this is sort of hooking this into the LangChain for J infrastructure. And I'm going to have some prompts. So I could have guardrails as well. So that is there. But here, this is you're an assistant in a pet adoption center. Your job is to help people find the right pet. So we've got a system message and a user message. If I go back here and I reload, then that is disappointing. Oh, I haven't changed my code. That would be why. So I have injected my AI helper here, but my code here is still just returning a dummy. So if instead I do return AI.pet with the preference, and then here I will return AI.pet. And so you can see one of the interesting things here is that this pet, it's returning objects in my domain model. It's not just returning strings or JSON that I would have to parse myself. I just say, I want a pet, and pet here is this record, and it gives me a pet, and it takes care of all of that. So now if I go back here, you can see that it's doing something, and I've got a fully hallucinated pet. So you can see this pet doesn't exist in the pet store, but that didn't stop the AI from providing it. If I was to do this properly, I would either want to have some sort of RAG backend, Or I would want to make it a bit more explicit that we're giving you a hypothetical pet that doesn't exist. And I can say something like, I would like an independent pet. And then we can get a cat. I can say I would like a fluffy pet. And we get another cat. I could say I would like something that is huge and fluffy, and I suspect I might get a Maine Coon again, because a Maine Coon is the... Oh, nope, I got a Newfoundland. So you can see, again, we're using AI integrated into the application in order to produce nonsense content. Value of that is limited, but it's not a huge stretch to see where this might be something that wasn't hallucination-based. So, and let me just close that. So that's that. Last demo, I want to show Minecraft. What I've done is I've taken all observability tools have sort of a similar principle, which is that you have your user code, and then you've got some sort of extensions, and then your client comes in, and then data is exfiltrated to your observability stack. And then you may not want to have a separate observability stack, so you may run it as a dev service. That observability stack doesn't need to be LGTM or anything proper like that. What you can do instead is you can use a much stupider observability stack, which is Minecraft. But it's the exact same architecture, it's just stupider. So, let me show you this. This, by the way, this is an official Quarkus, this is there's a Quarkus marketplace of extensions called the Quarkiverse, and my colleagues let me publish this as an extension there. So you can download this. It's a real thing. So let's go to the last demo. Let's start up in dev mode. So what this is going to do is this is going to start my to-do application, and is also in the background as a dev service starting a Minecraft server. So if I bring up my dev UI here, you can see I've got my dev UI, including my Minecraft client. And I can also have my application, so I can interact with my application. But where things get really interesting is when I hook up my observability client. So I have my client, and now I can see when things are happening in my application. I get a chicken with a timestamp, and then I can have events, and then I can. What happens if I create a duplicated to-do? Well, that is an error condition, so my chicken exploded, and I can do things as well, like I can change it so that instead of being a chicken, it is a pig. And then if I go back here and here, let's try reloading that again, and we get a pig. So we have live reload of the configuration of the observability client. And I am now very much at time. So let me just wrap up. This is all based on interceptors. You could do something that was actually useful with this. The dev services really helped a lot. I didn't need to manage my own Minecraft server. And I did an AI version, but we don't have time for that. So we've seen Quarkus uses about half as much energy as Spring Boot. We made a CLI that starts really, really fast. We used WASM so that we could run Quarkus that we could run Rust in Quarkus. We converted a Spring application to Quarkus. We had that really deeply integrated AI into our application, and we used Minecraft for observability. We covered a lot, and I think we just about got there. So all of the repos are there, as well as the slides. Thank you very much.